Hello dear students, welcome to Gate Wallah. This is Satish Kumar Durishetty, Faculty of Measurements and Instrumentation. Welcome to the next lecture in the one-shot series. In the previous lecture, we have seen the measuring instruments part 1. We have discussed elaborately about the PMMC. In this lecture, we are going to cover next instrument as a part of measuring instruments part 2. Okay, measuring instruments part 2. So after the completion of bridges, error analysis, PMMC, now we'll move to measuring instruments part 2, which is one of the important instrument. Today's class I am going to discuss on moving iron instrument. So fatafat, all of you please open your notebook, scribbling pad or anything and try to write down the short notes whatever I am giving. So this content is very important with respect to GATE examination and other exams, and almost all types of model problems I am covering. So in the previous lectures also I have covered number of problems. In this lecture also I am going to cover more number of problems for you. Chalo, we'll start. First we'll start with the constructional feature. Before that, there is the topics to be covered. Moving iron instrument construction. Next, it's the torque expressions. We are not deriving the expression, but we'll take the expression with respect to GATE exam. As I told you, for all the measuring instruments, torque expressions are very important. Sometimes those torque expressions are very close, easy to remember and somewhat confusing also. Okay, and range extension, definitely every instrument has ammeter or voltmeter. We have seen in PMMC. Here also moving iron can be extended its range. Last but not least, numerical problem. So first we'll start with constructional features of moving iron instrument. So this is the textbook diagram basically of the moving iron instrument. So the fundamentally moving iron instrument differs from the, if you see the moving iron instrument, it is internally is having not permanent magnet. The moving iron instrument basically is not having the permanent magnet, whereas our PMMC is having the permanent magnet. But moving iron is not having the permanent magnet. Moving iron is based upon the concept of normal a coil in which whenever a current is traveling, then what happens around this particular coil, a magnetic flux is going to be generated. And when there is no current, there is no flux. So as the magnetic flux lines are generating, then what happens? This particular coil behaves like a magnet. This coil is going to behave like a magnetic bar, north pole to south pole. When the current is traveling, it is going to behave like a magnet. So that's why this coil in which the current is passing is creating like a magnet. So this is called as electromagnet. What we call this as? We call this as electromagnet. This is the first difference with reference to PMMC. In PMMC we are using the permanent magnet, but whereas here we are using the electromagnet. In electromagnet, and the current is there, then only there is a magnetic flux. When there is no current, there is no magnetic flux. Now nearby this, suppose if a iron disc is attached. This is the iron disc. So then what happens? This iron disc is going to attracted towards this particular coil. So there is a deflection theta because of the current. The more is the current passing, then what happens? The more will be the theta, the more is the flux, the more is the flux in the coil, the more is the attractive force. The more is attractive force, this iron disc is going to move. So here the moving part is iron, not the coil. Okay na? So in permanent magnet moving coil, PMMC, what is the difference? In PMMC, so we are using the permanent magnet, and we are using the moving coil. The moving part is the coil. But in MI, in moving iron instrument, we are using electromagnet. And also we are using the moving part as iron disc. What is the moving part? We are using the iron disc. Moving iron. So around the coil, what happens when there is a coil, there is a disc. Imagine this marker as a disc. When the current passes through the coil, this coil will be having certain flux. This flux is having attractive force. Because of this attractive force, this iron disc will be attracted. So this attraction makes this iron to move like this. Suppose this is the iron disc. Let us take this is the iron disc here. So let us take this is the iron disc. So this iron disc is moving like this. This iron disc is moving towards, this is my coil, this my finger is coil. So this coil is experiencing the current, there is a magnetic flux. Then this particular iron disc will be attracted towards this. For this iron disc I am having a pointer. So when iron disc is attracted towards the coil, this particular pointer will deflect like. So this deflection is proportional to this deflection, and this deflection is proportional to attractive force. The attractive force is proportional to the magnetic flux. That magnetic flux is proportional to the current passing through this particular coil. So that is a basic concept here. So that's how the moving iron will work in brief. Okay. So whenever the current, this is a coil winding. So this is a coil winding. Let me explain. So this is a coil winding. A simple explanation I am giving. This is a coil winding. So this is a coil cross sectional view. So in this coil, suppose nearby there is a moving iron. Whenever the current passes through this, this iron disc will be attracted. This iron disc will be attracted to the coil. So then this pointer will deflect. Okay, na? So that means there is a change in self-inductance, because the iron disc is approaching means what? Iron is also having permeability, na? So when iron disc approaches to this particular moving electromagnet, this iron disc is approaching towards electromagnet, then what happens? Already electromagnet is having certain magnetic flux, it is also having certain self-inductance, na? So there will be a self-inductance change because of this iron disc approach. Why? Because when iron disc is approaching, the reluctance is decreasing. Previously there was an air gap, but because of this iron disc, what is happening? There is a change in reluctance. When change in reluctance is happening, then the change in self-inductance is also going to happen. Okay, so that is a fundamental feature. And remember, the most important point, it is suitable for both AC as well as DC. Why? Because if AC current is given, what happens? The polarity gets changed also. Only this magnetic polarities will change. This is the north pole, south pole. When AC current for the negative pulse, what happens? This will become south pole and north pole, but the same attraction force is going to continue. Yes or not? So that is the reason why moving iron instrument is suitable for both AC as well as DC. That is one point. And as it is a lightweight instrument, because we are using the electromagnet, not permanent magnet. For permanent magnet, we have to use the eddy current damping, but here we are using air friction damping. So the features you have to understand. So this is the deflection torque. The deflection torque is basically happening due to dl by d theta, change in self-inductance with respect to theta, and the damping torque, that is given by air friction damping that we are using. Next, the controlling torque is given by the spring. Dear. So these are the fundamental. Now, before entering to the next further section, let me talk about the torque expressions. So this is the torque expression. The deflection torque is given. The deflection torque TD, please remember this, I am not deriving, half I square into dl by dt. Try to remember, there is a deflection torque expression. So this deflection torque we can derive, but it's not necessary now. So deflection torque is given by this, and the controlling torque TC is given by Kc into theta. Okay, na? So that is the basic expression. In our PMMC also we are using the deflection torque bina controlling torque K theta. Okay, this current represents the AC or DC current, and this represents the change in self-inductance of the coil with reference to the deflection of the iron disc. Okay, so now at steady state what happens? So we can take the deflection torque is equal to controlling torque. So we can write half I square into dl by d theta is equal to AC into theta. So from this we can write theta is equal to I square by 1 by 2 Kc into dl by d theta. So from this, what you understand, theta is proportional to I square. Similarly, that is also can be written as theta is proportional to V square, na? So when it is proportional to that, then the scale is definitely a non-uniform scale. A non-uniform, actually it should be not linear, non-uniform scale. What is that? A non-uniform scale, because we are going to get the scale like this. So if you take this as the current and if you take this as the theta, for smaller values you are going to get, for smaller values you are going to get a crowded things, crowded readings. That means for smaller values of current the deflection will be very close, 0.01, 0.02, 0.03. For medium values that will be linear, 1, 2, 3 like that. But when current is increasing, theta is proportional to I square na, there is a spacious line. So that means here we are getting the crowded or cramped. Here we are getting the linear. Here we are getting the spacious. These are the spacious graph, spacious. And it is a non-uniform scale. It is a non-uniform scale. Non-uniform scale means what? It contains three set of things. It contains the crowded values, it contains the linear values, it contains the spaces. So you should not say non-linear. Actually some textbooks will say non-linear, because why? Because in that graph linear values are also present, because for the moderate values of the current you will get certain range, the graph will be exactly straight line. After that it will go spacious. Okay na? So that's why, dear students, you should say the moving iron scale is non-uniform. The PMMC scale is, got it? So these are the points about the moving iron. Now coming to the range extension, as I told you how to represent the moving iron. So to represent the moving iron, I will tell you the range extension of the moving iron. Range extension as ammeter first. Range extension as ammeter. How to represent it as an ammeter? So dear students, so this is the meter IM, but remember it is what? It is made up of what? It is made up of a air cored coil. It is made up of a electromagnetic type coil. So coil means definitely it is having some self-inductance and resistance. So I can take, this is the meter resistance RM and this is the self-inductance of the coil LM. So if I want to increase the range of this instrument measurable from IM to I, what should I do? I should do some attachment, yes or not? But what should be attached? That should be a shunt coil should be attached. So definitely the shunt coil, whatever that you are attaching, that also will have some resistance. As I told, it is having some resistance and also inductance. Just like in PMMC, we have attached shunt resistance. Here, for the coil of moving iron, we are attaching shunt coil. When I say shunt coil, it is having some shunt resistance. It is also having some shunt inductance. This is the shunt coil. Now the question is, what are the values of RSH? That is the question. Why? Because what should be the value of RSH and LSH so that the total current can be achieved passing through this I and this is I. Same methodology we can follow now. What is the methodology we have followed for PMMC? The same methodology we can follow here or not? What is that? See, we can say that this is the voltage across the coil. This is the voltage across the shunt coil. So we can say this VM is equal to VSH. Sir, VM is equal to VSH if we write. So this is IM, but here not RM. In PMMC only DC type, so RM. That is a coil only resistance, but it is wounded coil, air cored coil. Okay na? So here we are having some inductance. So we can write it as IM into ZM, right? This is ISH into, so ZM can be taken as what? ZM. Okay, Alice, I will write like this. IM by ISH is equal to ZSH by Z. This is the basic range extension as ammeter. Okay, so this can be further distributed. What is that? ZM is what? ZM means square root of RM square omega Lm whole square. ZSH is equal to what? RSH whole square plus like this. Okay, so now if I write Im by ISH, what I can write? If I take Rm square plus omega Lm square divided by RSH square plus omega LSH square. So this is the expression. Got it? So this can be simplified. How? Let me take Im by ISH is equal to square root of Rm square plus omega Lm square. This is Rm square plus omega Lm whole square divided by this is RSH square plus omega LSH whole square, and this is square root. Suppose if I am taking Rm square common, Rm will come out. This will be 1 plus omega Lm by Rm, right? Yes or not? Divided by RSH will come out 1 plus omega LSH by RSH. So now if you see, what is this Lm by Rm? That is the time constant of the meter coil. What is LSH by RSH? That is the time constant of the shunt coil. So if I am choosing such a way, time constant of the meter and time constant of the shunt both are same, what happens? That meter will be that meter is now independent of any frequency. Why? Because if I am choosing this time constant of shunt and time constant of meter as same, this term gets cancelled. Yes or not? So if it happens, Mi will be independent of frequency, is independent of frequency. That is the most important point. That is a beautiful point of moving iron industry. That means it is going to work like a DC. Whether it is a 0 frequency or 50 Hz frequency, we are going to get. But practically, can you get a shunt coil which is exactly having the time constant equal to meter coil? No. That's why in moving iron instrument there is an error. For different frequencies, you are going to get different readings. And same current of 5 amperes of 10 Hz, same current of 5 amperes of 50 Hz can give you a different indication. So that is what we call as frequency shift error. The moving error. So if time constants are equal, then what I can write, this Im by ISH can be equal to what, dear? Rm by RSH. Rm by RSH. As we want RSH, RSH will be again equal to what, dear? RSH is equal to Rm into, mistake we have done. Sorry, we have done a mistake, I think, here. Sorry, sir, we have done a mistake here, na? This. I'm so sorry. Mistake. Because this is ZSH by Zm means here ZSH should come, na? Opposite. This is RSH. LS. Okay. Rm. Okay. Right? RSH omega L. Always remember this M means this shunt opposite. This Rm. So this is RSH. This is Rm. This is 1 plus the LSH by RSH. Now finally, Im by ISH is equal to here. Get what? RSH by Okay, like PMMC expression, we are going to get a PMMC expression from this. RSH is equal to RM into IM by, okay na, perfect. This ISH can be taken as I minus IM. This ISH can be taken as I minus IM because I is only split into two parts na. So ISH, I is equal to IM plus. So from this we can take ISH is equal to I minus IM. ISH is equal to I minus I. So we can take RSH is equal to RM into IM. This is I minus. So if you take IM common, it gets cancelled. I by IM will come. So the same expression of RSH will come. That is RM into RM by M minus 1. Take this as IM. To take IM out here, this will be I by IM minus 1. This gets cancelled. So what we are going to get the expression as? The expression will be RSH is equal to RM by minus the shunt resistance. You understand? If you know the shunt resistance, automatically you can calculate the LSH also, because you can write like this. Time constant of the shunt and time constant of the meter are same. LSH by RSH is equal to LM by RM. So from this automatically you can find out the shunt resistance and so now you are getting all the things. Now you are getting all the things once you know the shunt resistance. You are getting the shunt component, and what is the shunt resistance? That is RM by, please remember this expression, M is equal to by, very important. What should be the components of the shunt to be attached across the moving iron ammeter so that its range can be extendable from 5 amperes to 100 amperes? Like that question. So these are the shunt components. So this is what the moving iron range extension as ammeter. Understood? Once again, in brief, moving iron can be extendable its range. So for that I am attaching a shunt element. So I am deriving the expression for the shunt element by using the basic voltages, parallel voltage are equal. You understand? And what is the advantage of this? At omega, suppose if we want to make independent of frequency, choose a element of shunt which parameters are matching with the parameters of the meter. But practically it's not possible. That's why there is an error. Similarly, we can follow the series resistance. How to extend? See, there's a printed also I have given for your reference. If you want to go for the range extension as a voltmeter, I can attach a series resistance here. So this also I will explain like this. So range extension for the MI voltmeter. So let me talk what is the range extension for the voltmeter. Okay, so first of all, what is the voltmeter diagram? So this is our IM, so this is our RM, sit, but there is a inductance. Now the voltage across this will be what? This is the voltmeter diagram na. But if we want to increase its range to V, then what should be done? We should attach a meter resistance, extra resistance. So this is our meter. So in series to this, I am going to attach a series resistor. If you attach a series resistor and if you take the total current I, so then this voltage will be V up to this. Understood? So now here also we can do the same analysis. What is the V? V will be capital I into Z total. Yes or not? What is the Z total? Because it is a frequency element. So I can take I into Z is what? Square root of Rm. Actually, what is this? Rm will be there in series, RSC is there plus J omega Lm. So what happens to Z total? That will be Rm plus RSC whole square plus omega Lm. Okay, na? And if you take Vm, Vm is only I into Zm, I is same. But here, this I will be square root of Rm square plus omega. Please remember, these only meter components. But whereas here, in addition to meter resistance, extra resistance should be added. So that is the RSC. So if you take the ratio of these currents gets cancelled, you can get the value of series. Okay, somewhat complicated, but remember it is dependent on the frequency. According to the frequency, you are going to get the RSC. That's what we have given. We cannot derive the expression directly. We cannot give the expression directly for RSC. So these are the equations for the RSC. Okay, so by using these expressions, we can also calculate the series resistance. But remember, this is purely dependent on the frequency. So that's why in series situation, what we'll do, as we are using the series resistor, definitely what happens for different frequencies, there is a different error is going to be possible, right? So to eliminate that error, we are using a capacitor here, using a capacitance. Okay, so across the series resistance, we are keeping a capacitor. So this capacitance will make you some elimination of frequency error. So that is the beauty of moving iron. By attaching a capacitor across the external resistor, you are compensating the inductance effect. You are compensating the inductance effect by attaching the capacitance, so that the frequency error somewhat reduced, and this capacitance value is given by expression 0.41 by L by RSC, the series resistance, RSC whole square. Okay, L is the meter's inductance, Lm by, very rarely asked question. What should be the capacitor value that should be attached in parallel to the series resistor, so that its value frequency error can be. So these are the most important things. One is a deflection torque, other one is a controlling torque, other one is a meter resistance, shunt resistance, meters inductance, shunt inductance, moving iron range extension as ammeter, moving iron range extension as voltmeter, and in voltmeter there is an error. To eliminate that error, we are using the capacitor. Okay, now before going to the problems, I want to talk about some basic errors. Every instrument is suffering with some errors, my dear, remember that. So first error is the hysteresis error, because it is an electromagnet type. Electromagnet type means what? When current is there, magnetic flux is there. When current is not there, magnetic flux should not be there. But practically speaking, no coil can have zero magnetic flux. A certain flux on a coil never dies. So that is the reason why what happens, even though for incremental current you are getting the incremental flux, but as the current is decreasing, the flux automatically cannot become zero. It will maintain some residue effect. That means even though there is no current, still there is a deflection is possible, certain cases. So that is called. Next, as it is a small coil, definitely it is a weak. As it is a weak magnetic field, external magnetic field can affect it, because in PMMC we are using the permanent magnet. Permanent magnet is strong, no external magnetic field can affect on it, but it is a weak magnet. Why weak magnet? It is electromagnet. Whenever there is a current, there is a magnetic flux. It is not a permanent magnet. So beside this particular moving iron instrument, if you are keeping any external magnetic field, definitely that also will go odd and some magnetic flux error. Okay, so coming to the advantages, it is suitable for both AC and DC. It is also cheapness and lightweight. Cheapness and lightweight. So these are the concepts, dear. So these are the concepts. Okay, so after the concepts, we'll start the numerical problems. Okay, so now it's a time based upon these formulas. Whatever the formulas I have mentioned, let me write. For Mi, Fatafat formulas I am writing because problems are important. Deflection torque formula 1 by 2 I square dl by d theta, my dear. Controlling torque formula kc theta, my dear. Next, theta is proportional to I square. RSH is equal to Rm by m minus 1. Okay na? For DC, for AC we have the condition of tau SH is equal to tau M. This is LSH by RSH is equal to LM by RM. All these things try to remember. So based on this, we will go for the numerical questions. Deflection torque, controlling torque, okay. Now based on this, we'll go for good amount of numerical questions. Chalo. Now we'll start the questions related to moving iron instrument. After the discussion of the working and its range extension and the torque expressions, it's the time to solve number of problems. In GATE exam and as well as in IAS exam, we are getting good number of questions on the moving iron. Let us see this question. The inductance of a certain moving iron ammeter. So question is related to what? Question is related to moving iron ammeter is 8 plus 4 theta minus half theta square microhenry, where theta is a deflection in radian from 0 position. This is most important. Theta must be units. The control spring torque is 12 into 10 power minus 6 Newton meter per radian. Calculate the scale positions in radians for 1 ampere, 2 ampere, 3 ampere and 5 amperes. So how to solve this question? First let me take the data. So what is given here? So if you see, the inductance is given as what? Let me write the solution here. So the inductance L is given as how much? 8 plus 4 theta minus half theta square. So this I can take it as 8 plus 4 theta minus half theta square microhenry. What is this? So this is microhenry. This microhenry. So first of all, let us take all the data given. Next, control spring is given 12 into 10 power minus 6. So control spring, that is given as 12 into 10 power minus 6 Newton meter. What is given? Newton meter per radian is given. Newton meter per. So first of all, what is the basic expressions of the deflection torque and controlling torque? If we write, the deflection torque expression is 1 by 2 I square dl by d theta. If this in, this is the deflection torque expression. Next, the controlling torque expression is AC into theta. So at steady state, so first of all, at steady state, the deflection torque and controlling torque both are equal. So what we can write, 1 by 2 I square dl by d theta is equal to kc into theta. So 1 by 2 I square dl by theta is equal to kc theta. Question asked here is, what is the value of the deflection? What is the value of the deflection for the different currents? First of all, to solve this question, we need to know the dl by d theta na? Yes sir. So what is the dl by d theta? To know the dl by theta, let me write here. So L is equal to 8 plus 4 theta minus, take here better, L is equal to 8 plus 4 theta minus 1 by 2 theta square microhenry. Yes or not? So then what is the dl by d theta? Is it visible? Yeah. If I am taking the dl by d theta, that dl by d theta will be 4 minus theta square means 2 theta, 2 gets cancelled. So 4 minus theta microhenry per radian. Why? Because these are the units of dl by d theta. So now let us use, for a current of 1 ampere is asking the deflection. So for if I is equal to 1 ampere, if I is equal to 1 ampere, For a current of 1 ampere, what is the theta he is asking? So how to calculate this? So I can take this as 1 by 2. So this is 1, and the dl by d theta expression is 4 minus theta microhenry per radian. So 4 minus theta microhenry per radian, and the Kc is also given in micros, 12 into 10 power minus 6 Newton meter per radian. So this is 12 into 10 power minus 6 Newton meter per radian into theta. So here comes the theta gets cancelled, so radian gets cancelled, micro and this 10 power minus 6 gets cancelled. So now if you simplify this expression, how much I am going to get? Let us check. So 4 minus theta is equal to 2 goes that side, 24 theta. So if you bring this 25 theta is equal to 4, theta is equal to 4 by 25. So how much I am going to get? So this is the expression here. So how much I am going to get? 4 divided by 25. So that is going to come as 0.16. Okay, 0.16 radian. Similarly, we can calculate for current 2 amperes, 3 amperes, 5 amperes. So let us move for the current of 2 amperes. So if I am taking, if I is equal to 2 amperes, if I is equal to 2 amperes, if I is equal to 2 amperes, then what happens? This 1 by 2, this is 4, dl by d theta, 4 minus theta, micro gets cancelled, and this will be 12 theta. So if we simplify, so this will be 2 2 ja, 2 4 8, minus 2 theta is equal to 12 theta, 14 theta is equal to 8. So theta is equal to 8 by 14. So how much we are going to get? So here we are going to get 8 by 14, means that is coming as 0.571 radian. 0.571. Have you seen? As the current is increasing, the deflection is also. Let us keep this in the box. Okay. Next, for a current of 3 amperes, and similarly for a current of 5 amperes, let us do it. Okay. So I am moving up. So for a current, if I is equal to 3 amperes, how much it is going to become? Half I square, that means it becomes 9. So this will be 4 minus theta as it is, and this will be 12 theta. Okay. So now if I am taking, this is 36 minus 9 theta is equal to 24 theta. So 36 is equal to 33 theta. So theta is equal to 36 by 33. Am I right? So if you check, 36 by 33 means it is coming around 1 plus 1.09 radians. 1.09 radians. Next we are going for last, I is equal to 5 amperes. So if I am taking I is equal to 5 amperes, if I is equal to 5 amperes, what I can write, 1 by 2, 5 square means 25 here, and this can be taken as 4 minus theta, and this is 12 theta, right? It's always 12 theta, right? AC, yeah, that is 12 theta. So this is 12 theta. So what I can write, 25 into 4, that is 100, minus 25 theta is equal to 24 theta. So 25 plus 24, 29 theta. So 100 is equal to 29 theta. So theta is equal to 100 by 29. 100 by 29 means you are going to get around 3.44 radians. Here the interesting thing about this problem is, not only the answers dear. Let us observe the value of the currents and the value of the deflection. Okay, so let me summarize. what we have got for I is equal to 5 amperes. So let me take more page. So let me take a table so that, so if you take the deflection and so this is, let us take as current and this as the deflection. Okay, so now if you check what are the readings we have for a current of 1 ampere, 2 amperes, 3 amperes, 5 amperes. Okay, so what are the values we got? For 5 amperes, 3.44 radians. We got this as 3.44 radians, and this will be 1.09 radians, 1.09 radians, and here check 0.571 radian and 0.16 radian, 0.16 and 0.16 is 0.16 and this is 0.571 in radians. Okay, so let me take this off, 0.44. Now if you check, what do you understand? My intention here is not only solving the problem, but if you see the readings, see the graphical representation of this particular, if you take x-axis current and y-axis if you take the deflection, what happens? So on x-axis I am taking the current, on y-axis I am taking the theta. So for a current of 1 ampere, let us take this as 0 and this is the 1 ampere, this is 2 amperes and this is a 3 amperes and this is the 5 amperes, like this. For a current of 1 ampere, I was getting 0.16 somewhere here. Next, for a current of 2 amperes, somewhat linear. See how it is moving. For a current of 2 amperes somewhere here, and for a current of 3, this, let us take this as 1 ampere. Okay, that is coming above 1.09, and for 5 amperes it is going very space. Yes or not? So that means what? The values are not linear. The scale that you are getting is not linear. First you will be getting a crowded, and so the scale is like this. So it is not exactly linear. So here somewhat you are getting a, here somewhat you are getting a crowded zone, and here you will get some linear zone, and here the reading for 5 amperes is going beyond the 3.44. Somewhere here it is coming 3.44. So here the reading are spacious. Okay, and here the readings are somewhat linear, and here the readings are somewhat crowded. Okay, so that means what? The scale is not a uniform scale. The scale that you are getting is not a uniform scale. So this is what we call theta is proportional to I square. So comparatively PMMC, this is a non-uniform scale. What is the scale? A non-uniform scale. Non-uniform scale, because you cannot say non-linear also. The moving iron contains linear. Why? Because theta is proportional to I square. So it contains what? It contains linear, crowded, contains crowded, plus it contains linear, plus it contains spacious. It contains spacious. Okay, so this is the point you have to understand. So this question intention is that. Okay, this question intention is not only just solving the problem. So what I have done in the question, he has given L. First I have calculated the dl by d theta, because the deflection torque expression of the moving iron is 1 by 2 I square dl by d theta. Kc is given. So first I have taken the dl by d theta here, and after that I have solved the problem for different currents. This type of problems or conceptual problems are very important with respect to your GATE examination as well as IS examination. Okay, chalo. Let us move for the next problem under the moving iron instrument. So this is the question number 3. The inductance of a moving iron ammeter is given by L is equal to 0.01 C theta whole square picohenry, where theta is a deflection from 0 position in degree. The angular deflections of the instrument corresponding to 1.5 amperes and 2 amperes are respectively 90 degrees and 120 degrees. Find the value of C. How to solve this question? This question is again related to the expression. So first let me take what is the data given. So if you take the data given, the L is given as, let us go for the solution. So what is the L is given 0.01 plus C theta whole square picohenry. Okay, na? 0.01 plus C theta whole square picohenry. So that is a L. So first of all, we know dl by d theta we have to find. So what is the dl by d theta? dl by d theta will be 2 times, this is 0.01 plus C theta, and brackets term if you derive with respect to theta, constant derivative 0, C theta will be C. Okay, na? So this will be picohenry per radian dear. This picohenry per radian. So this radians we have to convert into degrees. Okay, na? So this radian we have to convert into degrees. Is it clear or not? Yeah. This, why? Because dl by theta will be in radians, but here the deflections are given in degrees. Okay. So let me take one important point here. 360 degrees is equal to 2 pi radians. So from this 360 by 2 pi, that is 360 by 2 pi degree, that is equal to 1 radian. So 1 radian is equal to 180 by pi degrees. 180 by pi degrees is equal to 1 radian. So if we substitute that here, so dl by d theta expression will become as 2c 0.01 plus C theta. So this radian, if you take radian is equal to 180 by pi, 180 by pi, pi will go up, pi by 180 picohenry per degree. Understand? So this all is the conversion is required because our deflection is in degrees. So dl by d theta will be always Henry per radian. So this radians you have to convert into degrees. So the most important conversion factor here is 360 degrees is equal to 2 pi radians. Okay. So now let me take this particular dl by d theta as my basic expression which I can use for the further. Okay. So which I can use for the further. Okay. So what is our expressions? We know that deflection torque, continuation, deflection torque is equal to controlling torque at the steady state of the pointer. So what is the deflection torque? That is 1 by 2 I square into dl by d theta is equal to kc into theta. Right? So now let us go step by step. Two things. For current is equal to, what is given? For current is equal to 1.5 amperes. This is 90 degrees. For current 2 amperes, deflection is 120 degrees. So he is asking the C value. So what we have to do? Current value, if we substitute into expressions, you are going to get the theta value. So if you see, for a current of 1.5 amperes, for I is equal to 1.5 amperes, what happens to the above expression? So let me write green ink. That will be 1 by 2. I square means 1.5 whole square. dl by d theta we already have. That is 2c. Be careful. 0.01 plus C theta. 0.01 plus C theta. For what is the theta? For 1.5 amperes, the theta is how much given? 90 degrees given na. That is the logic. For current of 1.5 amperes, the theta is given in the question as how much here? 90 degrees. So substitute that 90 here. So this is a C. 90 degrees you have to substitute. Is equal anything missing? 2c 0.01 C theta into pi by 180. That is important. Pi by 180 picohenry per radian is equal to kc we don't know, and the theta is how much? That is a logic. Okay. Now similarly for a current of, for I is equal to how much current? Second current 2 amperes. For 2 amperes there is a deflection of how much? 120 degrees. For I is equal to 2 amperes there is a deflection of 120 degrees. So from this what I can do now? From this what I can do? Again I can write 1 by 2. Okay na? Okay, I will do one thing. Just I will keep this aside so that I can directly go for the division. Okay, so do one thing, just left side, right? So this I am taking it as one equation. What I'm taking it as equation 1. Okay, now for directly I'm doing the steps. Okay, so now for I is equal to 2 amperes, the theta is equal to 120 degrees now, given in the question. For I is equal to 2 amperes, deflection is 120 degrees now. So now if I substitute that, so these are 2 amperes, keep that 2 amperes here. So these are 2 amperes whole square. Okay, and 2C as it is. 0.01 plus C. So this is 120 degrees. How much it is? 120 degrees. And this is pi by 180 pico Henry per radian. That is equal to Kc into 120 degrees. So this is equal to equation 2. Equation 2. So now if I take the division of these two things, easy. Suppose if I am taking the division of this with respect to this, what happens? So I think some terms gets cancelled. Got it? I am directly writing the steps. For a current of 1.5 amperes, theta is equal to 90 degrees. For a current of 2 amperes, theta is equal to 120 degrees. So this is expression I have written. So now if I am taking the division of these quantities, what I am going to have? So this 1 by 2 gets cancelled. This 1 by 2 gets cancelled. 2C gets cancelled. 2C gets cancelled. Pi by 180 cancel. Pico Henry per radian gets cancelled. Kc gets cancelled. Kc gets cancelled. So simplified expression, 1.5 square means what, sir? 15, 15, 225. That means 2.25. So this will be 2.25 and 0.01 plus C90 divided by, this is 2 square. 2 square means 4. 0.01 plus C 120. Okay, so this 90 by 120 means 90 by 120 means how much, in short form? That is 3 by 4, I think. Yes, 3 by 4. Okay, so to simplify cross multiplication of this, you are going to get some expression. Okay, so let's complete this here itself. 4 into 2.25, I will how much? 4 into 2.25, that is coming as 9. So 9 into 0.01 plus C 90 equal to 3 into 4, 12. This is 12 into 0.01 plus C. Okay, so 0.01 into 9, that is coming a 0.09 plus 90 into 9, that is coming as 810 C equal to 12 into 0.01, that is 0.12 plus 12 into 120, that is coming as 1440 C. 1440. Okay, so I think now you are going to get 1440 minus 810, 630. 630 C. 0.09 minus 0.12 is coming as minus 0.03 minus 0.03. Okay, it can be negative, but it can be repulsive type moving iron, maybe it's maybe negative. By divided by 630 is coming around 4.76 into 10 power minus 5. So C is coming, the C value is coming around 4.76 into 10 to the power. Please take care of this. Please check the value once again. But I'm giving you the calculation part. 4.76 into 10 to the power. That is the value of C. Okay, so very good question, qualitative question, compared. What I have done, first I have taken the L, from that I have taken the dl by d theta. Okay, na? Next, dl by d theta, one important thing is we have to convert the dl by d theta units into degrees. They are given in radians. I have converted into radians to degrees. Next, for a current of 1.5 amperes, some deflection. For a current of 2 amperes, another deflection. Two equations when I solve, I am going to get this value as minus 4.76 into 10 power minus is the okay. Now based upon this sequence, actually we are following as per the sequence, as per our sequence of topics. So this is question number 3. Now I am going for 2, this is 3. Next I am going for question number 4. This is question number 4, d theta. Let us solve the question number 4. What is the answer? I think question is visible clearly. That is 10 plus 3 theta. Okay. So the inductance of a certain moving iron ammeter is expressed as, what is the expression given? L is given as 10 plus 3 theta, because 10 plus 30 cannot be given, printing mistake. 10 plus 3 theta minus theta square by 4 microhenry, where theta is a deflection in radians. Remember, theta is a deflection in radians. From the 0 position, the control spring torque Kc, the control spring torque Kc is given as how much? 25 into 10 power minus 6 Newton meter per year. No problem. This is given in radians, that is also given in radians, no problem. The deflection of the pointer in radian when the meter carries a current of 5 amperes. So when a current is equal to 5 amperes, so what is the deflection in? So how to solve this question? Before solving, let me take first of all the dl by d theta. Why? Because we need the dl by d theta. So let me take the dl by d theta first. So derivation of this 10 plus 3 theta minus theta square by 4 na. Yeah. So 10 plus theta means derivation of this will be 0. 3 theta means 3 minus theta square means 2 theta by 4. That's it. So this will be microhenry per n. Microhenry per. Okay. Let us move for the point. Sorry. Let us move for the expression. What is that expression? You can write deflection torque is equal to controlling torque. That is 1 by 2 into I square into dl by d theta is equal to Kc into theta. Yes. So let us use now this expression. What is the current value given? Current value is 5 amperes. So 1 by 2 5 square. Following na? Using the expression, number of times questions are coming, use them perfectly. So this is 1 by 2. This I square means 5 whole square. And what is the dl by d theta expression? That is 3 minus t by theta is equal to 2 by 4. 3 minus theta by 2. So this is 3 minus theta by 2. Units are important. Units are micro. So 10 power minus 6 I can keep. 10 power minus 6. And what is the Kc here? Kc is given as 25 into 10 power minus 6. So this Kc is given as 25 into 10 power minus 6. I think it's easy to answer now. Easy to answer. Okay. So 10 power minus 6 gets cancelled here. 10 power minus 6, 10 power minus 6 gets cancelled here. So this is 25, 25 gets cancelled here. Okay na? So if you simplify, this is 3 by 2 minus theta by 4. Okay na? Is equal to theta. Okay na? So 3 by 2 means 1.5. This is theta plus theta by 4. So 4 theta plus theta, 5 theta by 4. 5 theta by 4. So 1.5 into 4 by 5. 1.5 into 4 divided by 5. So I am getting as 1. What is the? Yes, perfectly. Option C is the answer. So theta is coming as how much? If you solve this, understand? Okay, let me take one more step. No problem. 1.5 is equal to 5 theta by 4. So from this, what is the theta? Okay, 1 second. 5 by 4. 1.25. 1.5 divided by answer 6 by 5. That is coming as 1.2 radians, because he is asking deflection radians, because we are taking the radians. 0.2. Okay na dear? So option C is the 1.2 is the followed. Very good questions. quality questions. Don't miss these questions. Very, very good questions. Question was asked in IIT Madras in 2003, dear. Question was asked in IIT Madras in 2003. Try to understand. The inductance of a certain moving iron is expressed by expression, and he's asking. Very simple. This type of questions will come. Comparatively previous was somewhat derivation and calculating the C value, right? But here he's asking directly from, he has set the numerical values so that easily you can do it. Simply, first L is given, find out the dl by d theta. Don't forget the units, microhenry per the radian. Next, current is given, theta is asking in degrees. So if you take that expression, controlling torque expression is same everywhere. So TD is equal to TC. If you substitute, you are going to get 1.2 radians here. Okay. Now let us move for one more question. Question number, see the sequence I am following as per my content sequence I am following, because questions may be in different order, but as per the sequence of teaching I will follow. Okay, that's why I have not written the question number. The thing is, I have derived torque expression. After that I have gone for the range, extension of the range of the meters, right? So accordingly I am choosing the questions. Okay, so this question was asked in IIT Delhi 2004. How to solve? Let me read the question. A moving iron ammeter produces a full scale torque of 240 micronewton meter with a deflection of 0 to 120 degrees. See here, 0 to 120 degrees at a current of 10 amperes. A current of 10 amperes. The rate of change of self-inductance in microhenry per radian of the instrument. See, the question is based upon the fundamental formula deflection torque. First, let me write. The moving iron ammeter produces a full scale torque of 240 micronewton meter with a deflection. That means he is talking about deflection torque. So the deflection torque is given as how much, dear? 240 micronewton. Good. Torque is given. Deflection of 120 degrees for a current. So for a current of 10 amperes, the maximum deflection goes to how much? 120 degrees. The rate of change of self-inductance is asking. So question asked is, what is that? dl by d theta is much. So how to do this question? Dear students, directly formula. Deflection torque formula is 1 by 2 into I square into dl by d theta na. 1 by 2 I square dl by d theta here. So deflection torque is given as 240 micro. That means 240 into 10 power minus 6. This is 1 by 2. And what is the current? Current is equal to 10 amperes. So this is 10 square we can take. And what is a dl by d theta? Now you can solve. Check the options. All the options are in micros. So don't cancel this micro. 2 will come here, 480. 480 by 100, 4.8. So the right answer for this question is 4.8 in 10 power minus 6 microhenry per, because always. So the right answer for this question is option B. So don't forget this working formula. That's why I kept in the initial lecture, I kept more importance for this deflection torque expression. Deflection torque formula 1 by 2 I square d by. If you followed now, very, very good questions. So now let us move for some extension of the range, because we have discussed with the range extension. Now we'll solve the questions on range extension. Let us move for the next question on the moving iron. This is the question. Question number 6. 3 moving iron type voltmeters are connected as shown below. Voltmeter readings are V, V1 and V2. So this is one voltmeter, this second voltmeter, this third voltmeter. The correct relation among the voltmeter readings is dash. This question was asked, actually it's a question combination of network theory, that is the IIT Bombay 2013 question. Remember this simple question, this V if you take it as a source and this is a current if I take, so this is the I can take. So first of all I can write V is equal to V1 plus V2. Am I right or not? Because this is the source voltage. If you take, right? One voltmeter moving iron is showing as a source, other voltmeters are connected in parallel here. So the voltage across this and the voltage across this summation should be equal to this. So what is the V1? V1 is equal to minus I into minus J1. So I can write minus J into I. J into I. So what is V2? V2 is plus 2J into I. Okay, so this is the expression 2J into I. Okay, so if you take the magnitude of V1, magnitude of V1 is equal to what? Square root of I square J square, so it will be I. And if you take the magnitude of V2, how much it will be? 2I. Okay, so V1, V2. And we know that V is equal to, what is V? V is equal to what? V1 plus V2. But if you take here the expression of V, how to get it? That is the combination of I into minus. So what is the V here? V is equal to I into minus J1 plus same current is going plus J2. Okay na? So that is coming as what? So this is coming as what? V is equal to I into plus J1. So if you take the magnitude of V, the magnitude of V is equal to I. Okay na? Magnitude of V is equal to I. So that means what is the relation now? We are getting this as I, this as 2I, this as I. That means what? The V is equal to I. That means it will be V2 minus V1 matching now. So V2 is equal to 2I and V1 is equal to I, then it is coming. Please try to understand. V1 is minus J into I, V2 is 2J into I, but whereas V is equal to same current I is crossing into the 2 meters, I into minus JY plus J2, so I am getting 1J. If I take the magnitude of VI, magnitude of V2 2I, magnitude of V1 I, so the relation between them is equal to 2I minus. So the right answer is V2 minus V1. So option D is the right answer for this question. Option D is the right answer for this question. D answer. Good question. Okay, chalo, let us move for the next question. Yeah, this type of waveform questions are very, very important. Question number 7 asked in IIT Kharagpur 2014. How to answer this question? Of course, it is a sawtooth waveform. This is a voltage 100 volts. The sawtooth voltage waveform is shown in the figure, fed to a moving iron. We know that moving iron measures the RMS value. So first of all, 0 to 20 milliseconds, what is this? We can find it out. Okay. So at a t is equal to 0, so by using the expression y minus y1 is equal to m into x minus x1. Okay na? So what is m? M is equal to y2 minus y1 by x2 minus x1. x2 minus x1. Based upon that, I can find out in between t is equal to greater than 0 and less than 20 milliseconds. 20 milliseconds. So in between, if you take the waveform, so what is the slope? Y. What is y? That is v. V of t minus. What is y1? 0. Good. M. y2 minus y1. What is y2? This is x1 y1. This is x2 y2. So this is 100 minus 0 volts divided by x2. 20 milliseconds minus 0. So 20 milliseconds. So this is milliseconds. This is volts into x minus x1. What is x? X is equal to t, x1 is equal to 0. Okay, so this is the milliseconds and the milliseconds get cancelled. So what I am going to get, v of t is equal to 100 by 20, that is 5. X minus x1. Sorry, sir, these milliseconds cannot be cancelled, right? This is volt per millisecond. Because here this is 20 milliseconds. Phi2 minus phi1, 100 volts, 0 by x2 minus x1, 20 milliseconds minus 20 milliseconds, x minus x1. X is equal to t. So we are getting it as V of t, we are getting it as how much? Milliseconds if you take, is coming as phi t volts, right? Getting it as phi t volts, right? Mistake we are done. V of t is equal to phi t volts. Yes, phi t. So now what is the integration? We can take the V RMS, that I can take it as 1 by t integration of 0 to t V of t whole square dt should be under, that is a VRMS. So I can take it as square root of 1 by t. What is the 1 by t? 1 by 20 milliseconds. 20 milliseconds means I can take it as 20 into 10 power minus 3, that is 2 into 10 power minus 2, that is 0.02. 0 to 0.2 seconds, that is V of t equal to what? V of t is equal to phi t, right? Right, any mistake I've done? 100 volts by milliseconds, that is slope, volts per millisecond slope. X minus x1, that is a time, that is also milliseconds, correct? Phi t volts. So this phi t whole square into, so now if I take this square root of 1 by 0.02, so phi square, that will come out as 25 integration of 0 to t 0.042 t square. Okay, so what is the value that we are going to get? Please check it out. How much we are going to get this? Check it out. This will be square root of t cube by 3 na, so 25 by 2, okay, cube by 3, 0 to 0.02 seconds. So if you simplify, going to get this as 2500 0.02 whole cube divided by cube by 3 to how much we are going to get? Let us check. Use the calci. So we are getting the answer as 0.057 volts. Getting the answer 0.057 volts. The answer is coming as 0.057 or 57.73 millivolts. Question asked is in volts na. The right answer is 0.057. Got it? So 0.057. The sorry, I think here units are not matching. This T unit should be there. This cannot be cancelled here, right? Because yes, some simple mistake we have done. T minus 0 is 20 is, can take it as 0.02. Okay, this one T minus 0 seconds. If you take now, seconds cancel, so this will be getting as 5000 T here. I did a mistake. 20 into 10 power minus 3, so 100 by 20, that is 5000. Perfect. 5000 T should come here. Then a mistake, sorry. 5000 T. 5000. Okay, please make it as 5000 T. Okay, this will be simplified as now 5000 T. Here the expression will be 5. Wrong. Mistake here will be 5000. Square root of 1 by 0.02, which is 5000 square, integration of 0 to t square dt. Simplify how much you are going to get. 5000 square divided by 0.02. Of answer 2. Square root of 5000 square divided by 0.02 t cube by 3 na, 0.02 whole cube by 3. That's it. Okay, 0.02. I will take other tip also, network theory, that is average RMS value of a sawtooth wave or triangular wave. Peak voltage by root 3, that is also one method is there, but this is the standard. 0.02 whole power 3 divided by 3 to 5000 to put answer by 57 point, what mistake, 57.7 volts. Or directly we can take RMS for this value from network theory is V peak by 3, that's V max by 2. Okay, so we can take V max by root 3, 100 by, that is coming as 57.7. Mistake here, so this is 57.75. Okay, these are the questions till now on the moving iron instrument. Now let us see some questions on range extension of the moving iron instrument. Okay, just like PMMC range extension, moving iron range extension also important. In the exam, we are getting the questions regularly. Now let us see this question. As per sequence is a question number 9, but I am following as per my teaching. Question asked in IIT Guwahati in 2018. What is the question? A 0 to 1 ampere moving iron ammeter, 0 to 1 ampere moving iron ammeter has an internal resistance of 50 milliohms, an inductance of 0.1 millihenry. Okay, a shunt coil is connected to extend its range to 0 to 10 amperes for all operating frequencies. This is important. For all operating frequencies means the moving iron is independent of frequency. The time constant in milliseconds and resistance in milliohms is asking for the shunt coil. That means is asking the shunt coil's time constant and is asking the resistance of the shunt coil. So first of all, question is related to moving iron ammeter. So let us draw the diagram of moving iron ammeter. So moving iron ammeter, how the diagram will be? See, this is our moving iron meter IM. Definitely it is having some internal resistance. So this is the internal resistance RM. Okay, na? And it is also having some internal inductance, that is the coils. Moving iron is made by electromagnetic coil, yes or not? That is a air cored coil. So it is having some self inductance. The self inductance is given as Lm. So now to increase its range, what we'll do? We have to attach a shunt. So when you attach a shunt, the shunt will be having what? The shunt will be having RSH and also it will be having LSH. Okay, na? So that the total range, if you are increasing the range current to I, so the current is split into this part, RM, LM, and one part, that is a meter current, and the shunt current is ISH. Now, question, what is the data given? Let us see first. 0 to 1 ampere moving iron ammeter means the range is up to 1 ampere. So let me write the data, whatever is given. So this is 1 ampere. Next, what is the meter resistance? The meter resistance is given as 50 milliohms. So this is 50 milliohms. 50 milliohms. And inductance of how much? 0.1 millihenry. So this is 0.1 millihenry. Next, extend its range to 0 to 10 amperes. 0 to 10 amperes means he is expecting this current I as 10 amperes. So question asked is the time constant. Excuse me. The time constant in and resistance. So first of all, he is asking the shunt. So he is asking this value. Of course, we have to know this value also. Excuse me. How to solve this problem? So if you see, these two are parallel, right? So these two are parallel. Even though current is divided as IM and ISH. Excuse me. So the voltage across them is same. So we can write the fundamental expression, voltage across the meter, voltage across the shunt, both are equal. So I can write this as IM into Zm, because impedance, because meter is having resistance and inductance, and shunt is, I can write as ISH into ZSH. Okay, so what I can write, IM by ISH can be taken as opposite ZSH by, okay, so if you extend, what I write, IM by ISH is equal to ZSH by, what is ZSH? If you take the magnitude, what is ZSH? That is R plus J omega. So we can write this as square root of RSH whole square plus omega LSH whole square divided by this. I can write RM whole square plus omega LM whole square. Okay, so now if I am taking this RSH whole square common, so this will become RSH whole square. If I take common, RSH whole square, if I take common, RSH comes out. and this will be 1. Is it visible to you all? So yes, RSH whole square, if I take common, RSH comes out 1 plus omega LSH by RSH whole square divided by RM square, if you take common, 1 plus omega LM by RM square. Got it? So now, in order to make independent of operating frequency, means for any frequency it has to work, means what is the condition? The time constant of the shunt and time constant of the meter must be equal. Okay, so at that time what happened? Tau SH is equal to tau M, so this term gets cancelled. Why? Because LSH by RSH is the time constant of the shunt, LM by RM is the time constant of the meter. At DC also it has to work, right? At DC also it has to work, means independent of all frequency, means for frequency 0 also it has to work, the meter. So omega is equal to 0 means, so we can take the time constants are becoming perfectly equal. Tau SH must be equal to tau M, then it will be independent of all frequencies. Okay, so tau SH is equal to tau M I have taken. Then what happens? Well, the equation will become as ISH IM by ISH is equal to RSH by RM. So from this we can write the shunt component. So this is a basic expression. So from this what I can write, RSH is equal to RM into IM by ISH. What is this ISH? From the previous diagram, this ISH is what? ISH is equal to, I is split into two parts now. I is equal to IM plus ISH. So from this ISH can be taken as I minus IM. Okay na? Shunt current. So that if you write here, so this RSH is equal to RM, this is IM. So if you take this as, this is the way you can derive, or if you take IM out, IM gets cancelled. So we are going to get RSH as what? Let me extend this diagram. So RSH as what? RM into this IM, if I take out here, this will be I by IM minus 1. So IM gets cancelled. So the formula for shunt resistance is equal to RM by M minus 1, where M is the I by M. So from this, just like our PMMC, in PMMC, a range extension of ammeter gives you the shunt resistance RM by M minus 1, where M is equal to I by M minus 1. So from this we can calculate now. So what is the RSH? Let me calculate RSH now. What is the RSH, dear? So what is the RSH? Fatafat. RSH. RM. What is the meter resistance, dear? The meter resistance I can take it as 50 milliohms. Okay, that is 50 into 10 power minus 3. M is equal to what? M is equal to I by IM. I is equal to how much? You have to change to 10 amperes. Yes, this is 10 amperes. And meter is what? Meter is 1 ampere. So 10 by 1. 10 by 1, that is equal to 10. So 10 minus 1. So 10 minus 1 means 9. So 50 by 10 minus 1. 50 divided by 9. So it is coming around how much? 5.55 milliohms. Is coming around 5.55 milliohms. So the shunt resistance value we are getting it as how much? The shunt resistance value we are getting it as 5.55 milliohms. So this is the shunt resistance value, 5.55 milliohms. But the question asked is one more, is also asking the time constant. How to find it out? So if you know RSH, what is the condition? You can find out the time constant of the meter. Yes or not? So what is the time constant of the meter? Time constant of the meter is equal to LM by RM. Time constant of the shunt is equal to what? LSH by RSH. LSH by RSH. So from this, if you equal the time constant of the meter must be equal to time constant of the shunt. So from this, what I can write, Lm by Rm can be made equal to LSH by RSH. Yes, dear. So from this, Lm is already there in the question. So you can find out the LSH. LSH is equal to RSH into Lm by Rm. Yes or not? So RSH already just before you have calculated, that is coming as 5.55 milliohms. So take this as 5.55 into 10 power minus 3 into what is Lm? That is the self-inductance of the coil, that is 0.1 millihenry. So substitute that 0.1 millihenry here. So this is 0.1 into 10 to the power of minus 3. And what is the Rm? Rm is the meter resistance, that is 50 milliohms. So substitute that here. So that is coming as 50 milliohms. So what is the answer? You can find out. 0.1 divided by 50, that is 1 by 500 into 5.55 divided by 1000 is coming around 1.11. Okay na? So LSH is coming as 1.11 into 10 to the power of minus 5. So time constant of the shunt is equal to LSH by RSH. So that will be 1.11 into 10 to the power of minus 5 divided by RSH is 5.55 into 10 to the power of minus 3 divided by 5.55 into 10 power minus 3 is coming as 2 milliseconds. How much is coming? 2 milliseconds. These are the values. Time constant value is 2 milliseconds and meter resistance is 5.55 milliohms. Let us check which option is matching. Option A is perfectly. Option A is the 2 milliseconds, and because question asked, very good question, qualitative question. Question was asked IIT Guwahati in 2000. See, first what I have done, when the question is declared as moving iron ammeter range extension, first of all directly I have gone for the diagram. Once you have conceptual understanding, there is no need to by heart the formulas. See, whenever that moving iron ammeter has to work for all the frequencies, means it also has to work for zero frequency. When it is working for zero frequency, what happens? It is like a PMMC. Why? Because for zero frequency means the inductance spots, impedance spots will be wave off. So directly we can take the RSH formula from the PMMC. RSH formula from the PMMC is equal to Rm by M minus 1, where M represents the multiplying factor of the current, I by Im. So I have done that. So from that I got the RSH. But question is asking the time constant also. Time constant of the shunt is equal to RSH into, LSH by RSH. So for that we need the LSH. How to find out the LSH? We need the basic understanding. The basic thing is time constant of the meter and time constant of the shunt must be equal. So by using that, Lm by Rm is equal to LSH by RSH. Everything is known. Lm is known to you. Yes or not? From this, what is known? Lm is known to you, Rm is known to you, RSH you got it. So you can find out the LSH. Once you got the LSH, once you got already the RSH, LSH by RSH will give you the time constant of the shunt component. Very, very good. Okay, got it? This is a beautiful question. The range extension. Be careful. Let us go for the next question. Now let us move for this question, question number 2 in your booklet, in your PDF. So this is a range extension of the moving iron voltmeter. Okay, question is related to range extension of the moving iron voltmeter. Let us see the question. A moving iron voltmeter for a full scale indication of 120 volts has an inductance of 0.6 Henry and a resistance of 2400 ohms. The instrument is designed for a frequency of 50 Hz circuit. Specify the series resistance is asked. So first of all, how to draw the moving iron instrument? See, Moving iron as voltmeter. The question is moving iron as voltmeter. So when you take the moving iron as voltmeter, the symbol will be, so this will be the voltmeter reading Vm. This is its internal resistance Rm, and it is its internal inductance Lm. So this total forms the Vm. Okay na? So this is with meter without the series resistance, just before we have discussed. But if we want to increase its range, what we have to do, we have to attach a series resistance. So this is the series resistance. Without series resistance, the voltmeter voltage, so this is the voltage, okay na? So this is the voltage. So this voltage is nothing but Vm, but whereas with the series resistance, the voltage will be, so this is the basic thing you have to understand. That's the diagram. Okay na? So what is the series resistance that should be added externally to the moving iron voltmeter so that the voltage range can be extendable from 120 volts to 600 volts. This is the diagram. Okay. Now let us talk about what is the values given here. A moving iron voltmeter has a full scale indication of 120 volts. How much this is? 120 volts. Has an inductance of how much? 0.6 Henry. Good. 0.6 Henry. And a resistance of how much? 2400 ohms. The resistance of how much? 2400 ohms. The instrument is designed for a frequency of how much? This is for a frequency of 50 Hz. AC frequency of how much? 50 Hz. Circuit. Specify the series resistance value to increase the range to how much? 600 volts. So how to solve? My dear aspirants, the current passing through the series resistor and the current passing through this meter, both are same or not? Yes or not? So first of all, let me write about the Z. What is the Z now? Z will be, actually total Z will be included this and this. But if you take the Zm, what is the Zm? Let me write the Zm. The meter Vm is equal to Im into Zm I can write na? Sir, Im into Zm you can write, sir. So what is the Vm? That is given. Vm is how much? 120 volts. Very good. I will write this as 120 volts. Im we don't know. Im we don't know. So this is actually I. This is actually I. This is Im. This is the current passing through the meter as Im. Okay na? So, but we don't know the Im. Okay, I don't know. Keep it is. But what is Zm? Zm is nothing but what, dear? That is Rm plus omega Lm, Rm whole square, A plus JB whole square na, A square plus Rm square plus L, Rm square plus omega Lm whole square. So now you can find out the Im now from this. So what is this? This is 120 Im. What is the meter resistance, dear? So meter resistance is given as how much? 2400. So substitute this. So this is 2400 whole square plus omega Lm. Omega means 2 pi f, 2 into 3.14 into frequency 50 Hz into what is the Lm? The meter self-inductance, that is 0.6 Henry. So this I can take it as 0.6 whole square. Okay na? So now if you simplify, how much you are going to get? 2 into 3.14 into 50 into 0.6. Square of it. Got something. Square root of with Yeah, it is coming 2407. So Zm I am getting as how much? 2407.4. Okay, 2407 ohms. That's it. So 120 is equal to Im into Zm. The Zm is coming as 2407 ohms. The meter current will be how much, dear? The meter current is 120 by 2407. 120 divided by answer, it is coming around 0.049 and 0.05 amperes. Very why? Because dear, how to calculate actually? I need this. What are you doing, sir? But remember, the current passing here and the current passing here is same na? So if you want to know this I, what is the I we can take, or what is the I we can take? V by Z. Yes or not? The total Z is this including. Okay. So now if we calculate, what is the I? This I and this Im both are equal na? Yes sir. So now what I can say, this is a meter current. So let me take one more step. Meter current is equal to 0.05 amperes, which is also equal to I. Why? Because for a voltmeter, the series resistance will be in series to the meter. Whatever the current passing into the meter, the same current also will pass to the series resistor. So total current is equal to same. The same current is traveling. But what is I actually? I is equal to total voltage by total impedance na? Total voltage by total impedance. So now if I substitute this is 0.05 amperes. What is the total voltage? The total voltage is equal to 600 volts. Why? Because the total range to which extent. So Z total we can find it out. The Z total will be what? The Z total will be coming as 600 divided by, it is coming around 12,000. 12,000. So this is Z total, and Z of the meter also we got it. Z of the meter also meters 2407 ohms. So this is 2407 ohms. See, what is Z total? Z total is nothing but what? If you see from the picture, the total impedance of this diagram is what, dear? This and this na. So what I can write here? The Z total RSC plus RM whole square plus omega LM. The Z total. Yes or not? Why? Because the total impedance is RSC plus RM plus J omega LM. We take the magnitude. Got it? So now we got the answer. The magnitude of the Z total is this. So what is the RSC? Z total is equal to Zm plus Rm RSC. So RSC is equal to Z total minus Zm. So that will be coming around 12,000 minus 2,407 is coming as 9,593. That means 9.6. Very good question. 9.6 kilo ohms. So these are the good questions on range extension of the. So don't miss these questions.